Hello everyone. In this video, I will introduce our recent work self-supervised learning for multimodal non-rigid 3D shape matching. Our method can obtain accurate correspondences for shapes represented by both meshes and point clouds. For the first time, our method enables multimodal non-rigid 3D shape matching under a simple yet efficient self-supervised learning framework. To this end, our method combines unsupervised mesh-based functional map regularization with self-supervised contrastive loss to couple point clouds and meshes. Our method is able to obtain accurate correspondences for both complete and partial meshes, point clouds, as well as correspondences across these data modalities. Moreover, our method is robust against noisy and inhomogeneously sampled point clouds that is commonly in real scan data. Through a variety of experiments, we demonstrate that our method outperforms existing state-of-the-art unsupervised and even supervised methods on challenging benchmark datasets and shows previously unseen cross-dataset generalization ability. The background and motivation of our work is based on this observation. Currently, existing unsupervised point cloud matching methods and mesh-based matching methods applied to point clouds for 3D non-rigid shape matching often produce unsatisfiable matching results as shown in this figure. One of the main reasons is that the geometric information of point clouds is more difficult to extract and analyze compared to well-structured meshes. However, mesh construction from point clouds is still an open research problem and typically requires manual effort. So, in this work we try to investigate how to transfer the geometric information from meshes to point clouds during training to close the matching performance gap of these two modalities. In the context of unsupervised point cloud matching, existing methods typically focus on learning more discriminative and expressive pointwise features from input point clouds. To this end, the pointwise correspondences can be obtained using nearest neighbor search in the feature space during inference. However, it is often difficult to design efficient unsupervised regularization loss terms to fully exploit the geometric information in unorganized point clouds. Another challenging is that how to make the methods to be robust against noisy and partial point clouds. Unlike unsupervised point cloud matching methods, unsupervised matching methods for meshes are typically based on the functional map framework that is theoretically well analyzed during the past decade. The main idea of the functional map framework is depicted in the left figures. Instead of finding pointwise correspondences, it encodes the correspondence information into a small functional map using a series of basis functions like the Fourier transform in the Euclidean domain. To this end, the functional map can be more easily regularized during training. However, the functional map computation is inaccurate for point clouds and it requires functional map computation and conversion to obtain final pointwise correspondences during inference, which limits its application for point clouds. In this work, we propose a simple yet efficient self-supervised learning framework to combine both functional map framework and deep feature learning. Specifically, our method combines unsupervised mesh-based functional map regularization and self-supervised contrastive learning to enable multimodal non-rigid 3D shape matching. Our framework consists of 3 components and 2 regularizations, which I will introduce in the following. The first component is the feature extractor, which is a Siamese network that can be used for pointwise feature extraction for both point clouds and meshes. And it is also the only learnable component in our framework. The second component in our framework is the functional map solver. It is a differentiable and non-learnable solver takes the pointwise features as inputs to obtain bidirectional functional maps for meshes. The obtained functional maps will be used to compute functional map regularization during training and to obtain final pointwise correspondences for meshes during inference. The third component in our framework is the deep feature similarity module. It aims to predict soft pointwise correspondence matrix between point clouds based on deep feature similarity. The predicted pointwise correspondence matrix is regularized based on the functional map regularization during training and binarized to obtain the final pointwise correspondences during inference for point clouds. To train the feature extractor, our functional map regularization is used to regularize predicted functional maps from meshes and soft pointwise correspondences from point clouds. Furthermore, we use contrastive loss to encourage the feature extractor to extract similar features for vertices in meshes and corresponding points in point clouds. Combining these two losses, our method is able to transfer the geometric information from well-structured meshes to less organized point clouds. To improve the robustness of our method, we augment the input shapes with random rotation and zero-mean Gaussian noise during training. We conduct experiments on shape-matching benchmark datasets and demonstrate that our method outperforms existing state-of-the-art axiomatic, unsupervised and even supervised methods in most scenarios. Moreover, we observe our method substantially outperforms previous unsupervised methods when it is applied for point clouds, and the matching performance gap between these two modalities is bridged based on the multimodal learning. More experiments are conducted to further evaluate our method. On the left table, we demonstrate that our method shows previously unseen cross-dataset generalization ability with much less training data. This advantage is based on the powerful functional map regularization and efficient multimodal contrastive learning. On the right table, we conduct experiment on the challenging partial shape benchmark dataset. Again, our method outperforms previous unsupervised methods, especially when it is applied for point clouds. Finally, we show some qualitative results obtained from our method for non-rigid matching of 3D shapes represented by both meshes and point clouds. We observe that our method can produce high-quality matching results even for noisy and partial point clouds. We believe our work would inspire follow-up works in the context of multimodal learning of 3D shapes.